Hey everyone, welcome back. Today we're diving deep into the ultimate showdown, Roman concrete versus modern steel. Which one is better?
Somewhere off the coast of Italy sits a slab of concrete poured 2,000 years ago, and it is measurably harder today than the day it left the mold. A parking structure built 40 years ago, using modern reinforced concrete, is already condemned, its internal steel rusting itself apart. This is not old technology losing to new technology. This is a failure mode modern engineers poured directly into the foundation under your feet. The two mixtures are built on opposite chemical philosophies. Roman maritime concrete, known as opus caementitium, combined volcanic ash from the Bay of Pozzuoli with quicklime and volcanic rock. Roman engineers packed this mixture into wooden forms right at the waterline and let the tide finish the job. When that mixture sank into seawater, a reaction began that a 2017 study in the American Mineralogist Journal finally explained in full. Salt water seeping into the concrete triggered slow growth of a rare mineral called aluminous tobermorite. That mineral does not just resist fracturing, it grows through cracks, sealing them with new crystal structure as fast as the ocean opens them. The architect Vitruvius recorded the base recipe in his text De Architectura, though even he probably never grasped that his walls were designed to grow stronger under attack. Modern, reinforced concrete, built under the American Concrete Institute's ACI 318 code, works nothing like this. Portland cement forms a shell around internal steel rebar, and the rebar carries the real tensile load. The moment moisture reaches that steel, it rusts, and rusting steel expands, sometimes past 6 times its original volume. That expansion cracks the surrounding shell from the inside, a failure engineers call spalling. Once spalling starts, exposed rebar sits in direct contact with oxygen and moisture, so it corrodes even faster than before. The cracks widen, more water gets in, and the whole cycle repeats itself at an accelerating pace. Unlike Roman concrete, every stage of this loop leaves the structure weaker, never stronger, and there is no chemical mechanism inside standard rebar concrete that reverses any part of it. The Federal Highway Administration has linked chloride-driven rebar corrosion to a large share of the nation's structurally deficient bridges, many failing decades before their intended 50 to 100-year service life. A modern seawall rated near 35 megapascals, fresh out of the form, can lose more than half that strength within years of corrosion, not centuries. The Roman pier at Portus Cosenus, by contrast, has taken direct wave impact for 2,000 years, and researchers from the University of Utah and Norway's SINTEF have measured its structure as effectively stable. So why did engineering abandon the stronger long-term recipe? Because Roman concrete cures over years far too slowly for the immediate tensile strength modern towers and overpasses require on day one. Rebar-reinforced concrete was never designed to outlast anything. It was designed to be fast and cheap, with durability treated as an afterthought, a trade-off now costing tens of billions of dollars a year in repair. Here is the actual reframe. That Roman seawall is not surviving, despite the ocean. It is surviving because the ocean keeps rebuilding it, one crystal at a time, while the concrete under your car right now is quietly building the failure that will eventually take it down.
Ancient tech or modern engineering? Which side are you on? Drop your pick in the comments, and I'll see you in the next one.